Hello everyone and welcome to ML Done. I hope that you're all enjoying this nice Sunday evening. So over here in Dublin it's kind of cloudy and you never know, in Dublin things can change almost instantly. Anyways, so today we're gonna continue with our talk regarding neural networks. But first, a simple recap. So we said that a perceptron is a very simple form of neural network, and then we said that in a perceptron, we linearly combine the features of our input, and then, depending on the sign of that result, we have a thresholding function that would output 1 if the sign is positive, and it would output -1 if the sign of that linear combination was negative. Now, we said that it's maybe a little bit not too understandable. So today we're going to look a little bit deeper, meaning that why do we have 0 as a threshold? Why do we say that if the linear combination is bigger than 0, we'll output 1. If it's lower than 0, we'll output -1. What is so special about that linear combination being equal to 0? And then we also talk about what is really happening when we linearly combine our input features. What does that represent, that linear combination? So let's just investigate this deeper and deeper. So if you look at here, we have a very simplified type of a perceptron. So basically here, your data has only one feature, one-dimensional, and that feature is called x1. And x0 equals 1 is nothing but your bias unit. And W0 and W1 are the weights. We have Z over there. If I want to show what Z is the linear combination of your inputs, right? So that would be W1 multiplied by X1 plus W0 multiplied by X0, which will be equal to W0. And I told you why we care about this guy over here, this x0 equals 1. Think about it. If you look at this equation over here, it is an equation of a line, right? If you think about it, you've got this nice line equation. The vertical axis is z, the horizontal axis is x1, right? And if you think about it, if I just draw one line over here, the slope of this line is controlled by W1. And the intercept, meaning that where it cuts through the z-axis, which is over here, this distance, which is minus something, it's a negative value, will be controlled by this W0. That is called the intercept of the line. So if you think about it, the intercept could actually control where that line should be in terms of high or down, right? And if you think about it, if with the same line, if I just erase this a little bit, make it a little bit neater, with the same line, if I were to just keep the same line as it was, right, with the same W1, but reduce W0 into a lower value, meaning that instead of cutting Z at this value, let's cut it over here. So it means that W0 is more negative, right? So then your new line would be here. Note that the first case, cut your x-axis here, but the second case, cut your x-axis here. We do care about that position where this line cuts through your x-axis for a reason. We're gonna dig deeper now and see why we care about that. Hint, that has something to do with that 0 that we're interested in, why we care about 0 being the threshold. Now, if you think about it, let's say you have 6 data points in your data sets. 3 of them belong to class green, say class positive, and 3 of them belong to class red, class negative. And since when we train a neural network, we start those weights randomly. And because z is an equation of a line, the starting point for our line is really, really bad. So if you think about this line is cutting your x-axis over here, right? Over here. Now, if you want to figure out how does this line classify your input data, if you think about it, anything that falls on this side of the line will be classified as the same class, and anything that falls over here will be classified as the other class. Why? For example, if you think about it, if I ask you, how does your classifier think about this particular data point? What you have to do, you have to see where it cuts through this line, and then look at the resultant z value, and then look at the sign of that. The sign is negative, so that thresholding function would consider that as the negative class. And if you think about this guy over here, again, if you go down, it cuts the line over here, and the resulting z value for that is again a negative value. Again, your classifier would decide that this point also belongs to the same class as this green guy over here, right? So what we're interested is to make sure that this line, instead of cutting x1 in that terrible point, we're interested in moving the line a little bit more where it really cuts through between those examples, right? So here it is. After we train our perceptron in a black box, I haven't talked about training a neural network. What happens is this line changes the slope and then moves to the right and then cuts our x-axis over here. Right? Where is this position? That is the position where z is, pay attention, your z is 0. What does that mean? That's the position where w1 x1 plus w0 is 0. You see? And that is the border which really separates your samples from each other. Right? So that is why we're interested in that 0 value. If your x data, please pay attention, if your data is one-dimensional, like in this case, your z is the line. If you notice, x is 1D, just points, one-dimensional, but z is a line, two-dimensional, right? So that z has one dimension extra, because it's a line now, right? But if I want to figure out where it actually cuts through my input space, that is where that z becomes 0. That is the border. That is where we're interested in, over here, that I just showed you over here, right? And if you think about it now, this line classifies this guy, and this guy. All of them would result to a positive value in z, right? If you look at the z value corresponding, say, to the first one, it's a positive value. The other one also positive, the other one also positive. And all of these guys on the left, if you think about it, this is where it cuts this line, and the corresponding z value is negative. So all the red ones will be classified as negative, the class negative, and all the green ones will be classified as positive, right? And the problem is, this line goes to infinity, right? We want to find a way to kind of crush this line into meaningful values, right? We want to make sure that for all the positive class samples, your neural network would generate one value, say positive value, and for all the negative samples would generate and say negative value. And that is why we've got that squashing step function over there. There we go. So if you look at here, the horizontal axis has changed from z to sine z, right? So right now we are at this point in our plot, this point. So in figure 1 and in figure 2, we were in this state. We were here. And now we are in this point, right? And that is when the output of your perceptron is either +1 or -1, right? So it limited that line that goes through positive infinity and negative infinity, right? And again, you notice this point is where we're interested in. This point. That is the point that dictates where should that squash our line to +1 and -1. That's the border line, right? That point is called the decision boundary, right? Now ask yourself, in one-dimensional data, our Z was a two-dimensional geometric figure, meaning a line. And we are interested in finding the best point, namely over here, that line cuts through our one-dimensional input space, which in this case, our decision boundary is what? It's a point. It's a 1D point, one-dimensional, right? What happens if we have two-dimensional data? Think about it. Before continuing with this video, ask yourself, if we have two-dimensional data, what geometric figure, what geometric shape would Z have? What geometric shape would our sine Z have? When you crush that Z, what would happen then? And more importantly, your decision boundary, how many dimensions would that have? Namely, is it a line? Is it a point? Is it a plane? What is it? Ask yourself that. Try to answer that before continuing with this, with the video. Right, for those of you who figured out the answer, congratulations. It means that you've really paid attention. For those of you who couldn't, that's fine. We'll figure it out together. Okay, now here our dimensions are x1 and x2, right? So we have two dimensions here, two features. And x0 is 1, again, we always have that bias unit. Now, if I ask you what our Z would be in this case, Z is equal to W1 multiplied by x1 plus W2 multiplied by x2 plus W0. Hold on a minute, this just sounds weird, right? It is not a line. It doesn't look like any line that I've met before, right? This is actually a plane. You've got x1 and x2, two dimensions, right? And the third dimension is your Z. And this equation is actually a plane, right? Now, if you think about it, you have two dimensions. A plane is three-dimensional, right? A plane is a three-dimensional geometric figure, right? So if you think about it, so this is your x1, that is your x2. You have 3 points belonging to class positive, 3 points belonging to class negative. Again, remember each one of these guys, each one of these data points has x1 over here. This is the value for x1. And if you go cut through to x2, that would be the value for x2 for that one data point. So remember that your data points are two-dimensional. Now, because Z is a plane and because we generate those weights randomly, the initial plane that we're going to have is going to be really terrible. Again, we're interested in finding the place where that plane cuts through our input space, which in this case is two-dimensional, x1, x2 plane, right? Where does that three-dimensional plane cut through our input space? We want to make that cutting boundary as good as possible, something that separates our examples perfectly. Now, if you look at it here, now think about this plane. This is just going in three-dimensional space, and somewhere it cuts through x1, x2, our input space, right? Now, where is that cutting place? That would be this dashed line over here. Look at it. This is where the plane cuts through our input space. Now, if you think about that line, is it really doing a good job in separating our examples? It's not. Actually, it's doing a terrible job. After you learn the weights, something nice happens. Look what happened. The plane rotated. And look at this line. This line just beautifully separates our examples. Again, please try to look at this from a three-dimensional space. Three-dimensional perspective. If I ask you, what is the value of z for, say, this point over here? You have to, this is kind of tricky. This is behind that yellow plane. This plane is going up, right? This is just going infinitely positive. You have to go up, until it hits the plane. And then connect that to the z vector, to the z-axis, and read that value. That would be the z value corresponding to that point. Now, if you think about, I know it's a little bit tricky, but this is the best way that I've been able to teach that so far. If you think about the z value for this data point, you have to let that plane go down, 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 and until this cuts somewhere through that yellow plane, and then you have to connect it to your z value somewhere down here. Like, so if you continue your z-axis down, 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 it will cut somewhere the z-axis, which would be a negative value, right? So this is the same story that we had with the line in the previous slide. So if you think about it, we have this plane that goes to positive infinity and negative infinity. That is why we have that squashing function to kind of limit the values of z. Right, look at this. This is beautiful. Now this is more understandable, I think. Now, if you think about it, if you connect, if you ask yourself, where does this plane cut the sine z axis? Remember, now we have sine z, right? Because the thresholding function just squashed our plane. So this cuts our z over here and +1. And down here, if you continue our z, this would cut through our z at this point, which is -1, right? So remember, this half of this squash plane is on the positive side of your vertical axis, and half of it is on the negative side of your vertical axis, sine of z. Okay. Now, if I were to ask you, what is the, say, value, the output of this perceptron for this data point? Remember, it is behind this plane. It's a little bit hard to imagine, but if you kind of go up, it kind of cuts through the top part of the plane somewhere around here. And then if you read the corresponding value on the z-axis, as I said, the top part of this squash plane cuts through your sine of z at +1. So the value that will be returned by your perceptron for that data point would be +1. And if you think about the value that will be returned, say, for this guy over here, you have to go down, 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 down until it hits somewhere around here. Cuts through the plane. Now that value is on the negative side of sine value. It's down below. Now if you connect it to the sine z vector, the sine z axis, it will cut through -1. So as you can see, for all the points, all the red points, the value that will return would be +1, and for all the points on the negative, and the green points, the value that will be returned by your perceptron would be -1. Again, if you notice, you are dealing with a two-dimensional data, right? And Z became three-dimensional, but where Z cut through your input space is a line, and that line, my friends, is again two-dimensional. Right? So remember, again, that line is where your Z is 0. That is where Z is 0. Okay? So we are looking for where is Z 0? We want to find the best place where Z is 0, because remember, Z is 0 here as well. Here again Z is 0, right? But the but that's a terrible decision boundary. But here in figure 3, again Z is 0 over here. But look how beautifully that line can separate your positive and negative examples. I hope that this has been informative for you. In this video, we talked about the idea of perceptron in more depth, and we tried to analyze the meaning of Z, that linear combination, in terms of a number of dimensions, and in terms of the geometric meaning behind it. And then we explained how that squashing function would kind of squash that Z into a shape that would pass +1 or -1 for the examples. And we talked about how that Z would cut through your input space and would create that decision boundary. And more importantly, we said that when the data is one-dimensional, the decision boundary is also one-dimensional. When the data is two-dimensional, the decision boundary is again two-dimensional. Now, my question for you, if we have three-dimensional data, what would be the shape of our Z? Is that a point? Is that a plane? Whatever it is, it has 4 dimensions, right? Because Z has always one dimension more than your input space. And a 4-dimensional Z is nothing but a hyperplane, right? So then you cannot visualize that anymore, and that is what we call a hyperplane, okay? And that is when things become more and more complicated, when we get to more and more sophisticated neural networks. But these were very simple examples to give you the idea as to what's really happening behind that linear combination and that squashing idea in a perceptron. So I hope that this has been informative for you, and until our next talk, take care of yourselves and goodbye.